Hello students, welcome to this module, which is part 6 in our series on differential equations. In this module I'm going to discuss the solution of differential equations, partial differential equations using integral transform methods. These are typically integral transforms, as you know by now, are for example Fourier transforms, which are suitable when the domain ranges from minus infinity to plus infinity, and Laplace transforms, which are applicable when the domain is one-sided, in the sense that 0 less than x less than infinity, so it is semi-infinite in some sense. Okay, so Laplace transforms are usually used to solve initial value problems. That is, you use Laplace transform to transform the time variable t, but in this module you will see an example where Laplace transforms can be used for a semi-infinite problem in the spatial direction. Okay, so the key idea is, again, the domain is semi-infinite, so it ranges only from 0 to infinity, much similar to what typically you have for time, which is bounded from 0 typically in initial value problems. Okay, alright, so now first I'm going to discuss the first example, which is that of, I want to solve unsteady heat conduction equation. Unsteady heat conduction equation. Alright, and suppose you have an infinite rod, okay, and you are interested in the, suppose this is the x direction and this is the origin, x equal to 0, this is plus infinity, let's say, and this is minus infinity, and you are interested in understanding, suppose I give over this rod an initial temperature profile. Let's say I'm using the variable u at time t equal to 0, you give some initial condition, and that initial condition may be something like this. Okay, the only key criterion is that the initial condition should not be diverging, it should be reasonably bounded as x goes to plus or minus infinity. This is x, this is negative x, this is minus infinity. So this is the initial temperature profile or initial condition. Okay, now once you have this, impose this initial condition where u of x tends to infinity at t equal to 0 is not unbounded, doesn't diverge or something. Then we would like to ask the question, how will the temperature change as a function of x and time as for this given initial condition. Okay, now of course we have to specify boundary conditions, and the boundary conditions are such that u of x tends to 0 as x tends to plus infinity, 0, and as x tends to minus infinity. These are the boundary conditions. Okay, so now the governing PDE, the partial differential equation that governs unsteady heat conduction, as you all know, is equal to partial u partial t. U is like a temperature, if you want a heat transfer analogy. Alpha squared is the thermal diffusivity. Okay, now the key idea is here is that the domain is unbounded. Okay, domain is unbounded. When the domain is unbounded, we cannot use eigenfunction expansion in the traditional sense, because those are typically eigenvalue problems are obtained for finite domains. Okay, so that is the reason why we already discussed while discussing Fourier series that we cannot use Fourier series for for domains that are unbounded, and therefore we came up with the notion of Fourier transform. So that's what we are going to use. We are going to use Fourier transform to solve this PDE. Okay. So now what we need to do is definition of Fourier transform is u tilde of k t is nothing but minus infinity to infinity u of x t e to the minus I k x dx. Okay, and if this is the Fourier transform, the inverse transform u of x t will be like 1 over 2 pi minus infinity to infinity u tilde of u hat of kt e to the plus I k x dk. This is the Fourier transform pair. Okay, let me write it properly. This is the Fourier transform pair. Now what I'm going to do is Fourier transform ft for short the entire PDE. This PDE which we have, right? This is the PDE that we have to solve. Alright, we have to solve Fourier transform this PDE, and to do that you have to integrate the entire equation by multiplying it by e to the minus I k x and integrate over dx. Okay, so let's show that here. So alpha squared integral minus infinity to infinity partial squared u by partial x squared e to the minus I k x dx. This is on the left side, is minus infinity to infinity partial u partial t e to the minus I k x dx. Now this side you have to integrate by parts twice because you have a second derivative twice. That will yield partial u partial x e to the minus I k x evaluated at minus infinity to infinity minus the second integration parts will give you u times minus I k times e to the minus I k x minus infinity to infinity plus minus infinity to infinity u of x t minus I k e to the minus I k x dx. This will be the left side. Okay, the right side will simply, you can take this right side, right, that will give simply, you can pull out partial t because the integral is only over x. So partial t minus infinity to infinity u of x t e to the minus I k x dx, and you know that the thing in the shown region is nothing but u hat of kt. This is the Fourier transform, definition of Fourier transform. Okay, and likewise if I look at this expression, okay, let me go one by one in this part of the equation. So the right side is very simple. This is nothing but, so this entire thing will be partial t of u hat by partial t. This is the entire right side. The left side, if you know that we have assumed that u behaves reasonably as it decays to 0 as x goes to minus and plus infinity. E to the minus I k x is just bounded function between minus 1 and 1. K is a real number, so this is 0 on both the boundaries, and similarly this is also 0. You assume that it also decays such that the slope of the function also is 0 as x goes to minus infinity and plus infinity. On the other hand, this expression out here, you have this, okay, you have these two, okay, which can be pulled out, right, and this is nothing but minus ik times minus ik is minus k squared. So let me write this as, so this is basically minus k squared. And what is the rest? So I can pull this also here, okay, and what is this? This is nothing but, this entire thing is again u hat of kt. Okay, so taking the partial differential, taking the Fourier transform of the entire PDE finally results in the following expression. Now when I look at this expression, the differential equation is now only in time, okay, you will see shortly. So you can safely replace this by du hat dt instead of the partial derivative, okay. So you have du hat, okay, let me write the left side. The left side had minus k squared times u hat of kt. The right side has du hat by dt. Because insofar as this equation is concerned, there is no derivative with respect to k, we can think of this as an ordinary differential equation in time, although it's a function of two variables, okay. So what have we accomplished by doing a Fourier transform? The original PDE in two variables, x and time, is now converted to an ODE in time, and the derivative, partial derivative, has now become simply minus k squared times u hat of kt in the transformed plane. Okay, so this is the simplification that one achieves. Now once you understand this, this is simply an ODE in time, and you can solve this very easily. U hat of kt is nothing but some constant e to the minus alpha squared. Okay, I'm sorry about forgetting this alpha squared, minus alpha squared k squared. Okay, so let's keep this alpha squared here as well, okay, on the left side. So it's e to the minus alpha squared k squared t. Okay, now this has to be fixed using initial condition, and now we were given the initial condition in u of x time t equal to 0 as f of x. This is a known function. You are prescribing what the function is at time t equal to 0. So we have to take the Fourier transform of the initial condition, so which will give me u hat of k t equal to 0 is minus infinity to infinity u of x t equal to 0 e to the minus ik x dx. But we know that u of x at t equal to 0 is just f of x. So this is nothing but the Fourier transform of f of x, which is f hat of k. So u of k t equal to 0 is known because we know f of x, so we can find what is f hat of k using the Fourier transform. Okay, so u of k t is nothing but, if I use this initial condition out here, now if I put t is equal to 0, this becomes 1. So a becomes simply u of k at time t equal to 0, which is what we found as f hat of k right here. So u hat of kt is f hat of k e to the minus alpha squared k squared t. Now if you are interested in only the Fourier transform, you have solved the problem, in the sense that this function satisfies the transformed differential or ordinary differential equation and the initial condition. But to find u of xt, you have to do inverse Fourier transform. Okay, let me illustrate this. Now in order to find the inverse, you have to understand that these are products of two functions. Okay, this is also a function of k. This is e to the minus alpha squared k squared, that's also a function of k. Now the inverse Fourier transform of products of two functions of k is given by minus infinity to infinity f of z g of x minus z dz. This is called the convolution theorem in Fourier transform. You must have heard of a convolution theorem in Laplace transform. Here g of x is the inverse transform of g of k. Let's put f hat of k, okay, g hat of k, and f of x is inverse transform of f hat of k. So we have products of two functions in the Fourier space. In the real space, the Fourier transform looks like an integral, inverse transform looks like an integral of the products of the two functions in real space with, okay, this as the dummy integration variable. The eventual function, the product will be a function of z alone, because you have only once you integrate, sorry, x alone. Once you integrate over z, you have only x. Okay, so now in our case, f inverse of f of k, we have two functions, right? F of k and e to the in this expression we had two functions. So we know what is the inverse of f hat of k, which is nothing but f of x, the initial condition, which we know. Okay. Now the Fourier transform, or sorry, the Fourier inverse of e to the minus k squared alpha squared t, such a function is called a Gaussian function. Okay, that is well known. So it's 2 alpha root of pi t e to the minus x squared by 4 alpha squared t. Okay, so once you know this, we can find out what is u of x t using the convolution theorem, because we know the two pieces. We know what is f and what is g. We have just found out in this particular case. F inverse of f of k is f of x. F inverse of this is just this. So u of x t is nothing but 1 over 2 alpha root pi t. The integral is only over x, so I can pull out time. Minus infinity to infinity f of z e to the minus x minus z by 4 alpha squared t dz. That's it. This is the formal solution to the problem. Okay, if you are interested in a general solution, that's it, you have solved the problem. Okay, just give me a minute. Okay, if you are interested in just the general solution, and you are done, you have the solution right in front of you. You give me what is you prescribe. Okay, you prescribe what is f of z, and then you know the solution to the problem. Okay, so this is the general solution without giving the specific functional form of f of z or f of x. Okay, z is just a dummy variable. Alright, now let's consider some special cases. Okay, we take a new page. Now I'm going to take a special case. The special case being, I'm considering an infinite rod. Okay, the initial temperature profile, this is x equal to 0, x tending to plus infinity and x tending to minus infinity. The initial temperature profile is going to be like this. It's going to be like this. You have 0 temperature for x less than 0, and you have some finite temperature, let's say capital F, for f x greater than 0. So this is 0, and this is some f. This is my f of x. versus x is like a heaviside step function where the jump is of magnitude f at the origin. So my u of xt will therefore become, for x less than 0 there is no value of the initial condition, so I have to integrate the integral that we just wrote down only from x equal to 0 to infinity. Minus infinity to infinity, the answer is 0. Okay, so the initial condition is 0, that is. So u of xt is nothing but 0 to infinity. Okay, let me write 1 over 2 alpha root pi t, 0 to infinity. Now f can be pulled out, that's a constant, so e to the minus x minus z the whole squared by 4 alpha squared t dz. Now we have to integrate this. So to integrate this, let's change variable. Let eta be x minus z by 2 alpha root t, then d eta is minus dz by 2 alpha root t. So u of xt is nothing but now this minus sign will come out, minus f by 2 alpha root pi t. Now the limits will change, because when z is 0, sorry, when x is 0, eta is minus, I'm sorry, when z is 0, eta is x by square root of, here z is the limit. Okay, I have to put z 0, then eta becomes x by 2 alpha square root of t. Now when z is infinity, then eta becomes minus infinity, okay, for a finite x. So and this becomes just simply e to the minus eta squared. Okay, and now dz by 2 alpha root t is nothing but or you can say it like this, dz is minus d eta 2 alpha root t, and that 2 alpha root t will cancel with 2 alpha root t here. Okay, so let me just write it down, e to the minus eta squared, minus is pulled out, 2 alpha root t d eta, this is nothing but minus f by root pi integral x by 2 alpha square root of t to minus infinity e to the minus eta squared d eta. Now I can change the limits by pulling out a minus sign, and that minus will cancel with this plus f by square root of pi minus infinity to x by 2 alpha root t e to the minus eta squared d eta. This is u of xt for this specific initial condition. Okay, now this can be further simplified as follows: u of xt is f by root pi times minus infinity to 0 e to the minus eta squared d eta plus 0 to x by 2 alpha root t e to the minus eta squared d eta. Now this is a very straightforward integral to do. It's again called a Gaussian integral. You can look up textbooks which show that what is this, and this one. Now once I have this, I'm going to write u of xt as, I'm going to pull out this root pi by 2, so root pi will cancel with this root pi, 2 will come out, times 1 plus, since I pulled out root 2 or root pi from the entire bracket, so I have to write this as since I pulled out root pi over 2, I'm sorry, then I'll have to multiply this by 2 over root pi integral 0 to x by 2 alpha root t e to the minus eta squared d eta. Now this object out here, is called the error function. The error function of any variable some z is equal to 2 by root pi integral 0 to z e to the minus let's say y squared dy. Y is a dummy variable that's getting integrated over. So here it's the same format. Instead of z, you have this. So we can conclude that u of xt is nothing but f by 2 1 plus error function of x by 2 alpha root t. Okay, this is the solution to this problem that we started off by assuming that the initial condition is like a heaviside step function of jump f. Now if I plot the error function of x as a function of argument x, it looks like this. Okay, now therefore if I plot the evolution of the temperature, okay, initially it was like this. Let's say this is, okay, let me draw it properly. Sorry about that. Okay, let me draw it in the next page properly. Okay, so you have, let's say this is your axis where you're plotting let's say u, right, of xt versus x at different times. Okay, so let's call this f by 2, and let's call this as f. Now at time t equal to 0, it's 0 here, so let me draw all the solutions in for time t equal to 0. It's 0 up to here, and then it takes the value of f. Okay, as time increases for small times, it will look like this. For large times, it will look like this, and eventually the answer will be, all the temperature will be, okay, okay. So initially the temperature profile was like a step function. This is at time t equal to 0. Now at times, let's say t is equal to t1, which is slightly greater than 0, the temperature profile will be like this, and time t equal to 0, it will be t2, sorry, it will be like this, and eventually as time t goes to infinity, okay, the temperature profile will become flat. That is, the nature of diffusion is to remove any discontinuities. That's the definition of diffusion, right? So if you have a step discontinuity of temperature or concentration, okay, of jump f in the domain minus infinity to plus infinity, eventually the nature of diffusion is to equalize all the temperature or concentration everywhere to f by 2. That's what this solution is trying to tell you. Okay, now this is one particular example. Okay, now let's think of another example, rather another limiting case of the solution, or a special initial condition. Remember that we wrote u of xt as 1 over 2 alpha root of pi t times minus infinity to infinity f of z, right, e to the minus x minus z the whole squared by 4 alpha squared t dc. Okay, now if I bring this in, let me do a little bit of rearrangement of this particular expression. Sorry about this. Okay, let's rearrange this expression slightly. I'm going to pull this in also. Okay, now if you look at this expression, okay, now I'm going to mark, okay, let me remove this term. This term is called, you can think of it as a kernel. It's called kernel, KERNEL. Now this is a function of only z minus x or x minus z and time. Okay, and this integral is over dz. Now all the information about initial condition is in this. Okay, so remember, you are trying to solve this problem. Subject to initial condition is f of x. Now this z is actually the dummy variable for x, right? Now all the information about initial condition is here, whereas all the information about how the system is going to evolve from the initial condition to the eventual steady state is here. So you can write this as u of x t as minus infinity to infinity f of z k of z minus x t dz. Okay, z minus, let me write it properly, xt. Now let us take a special initial condition where f of z is nothing but delta of z minus z naught. That is, you have a pulse, a delta function input, that is, you just have a pulse, a sharp pulse. Okay, imagine this is like injecting, at time t equal to 0, you are inputting it's like injecting, if you have a tube and then of some water, and then at time t equal to 0, at x equal to 0, you are injecting a momentary pulse at time t equal to 0, and then you are interested in seeing how this pulse is going to evolve as a function of time. It's like, literally speaking, it is like getting an injection shot from a doctor, where the doctor intravenously injects some medicine into your body, right? So it is like that. So you are interested in seeing how that special initial condition, a delta function pulse, is going to evolve as a function of time. Okay, so what is u of x t minus infinity to infinity? Instead of f of z, I am going to put delta of z minus z naught. Now k of z minus x t dz. Now the property of delta of function is that f of x minus x naught, delta of x minus x naught, f of x dx over the entire domain is f of x naught. Okay, likewise, that is the nature of delta function. When you integrate the delta function with some other function, the delta function is going to pick out that value of the function at the point where the delta function is picked. So here u of x t will become, here this is going to pick, instead of z, you are going to pick z naught. So this is nothing but k of z naught minus x t, and k is an even function. Okay, you can look at the kernel, it's an even function, so it doesn't matter whether you write it as z naught minus x or z x minus z naught t. Okay, so what we are saying is that the kernel that we identified here is actually the solution to the governing unsteady heat equation to a delta function input. Okay, now this z0 can be 0 also. Okay, that doesn't matter, that just tells you where the delta function is peaked. Okay, so if the delta function is like this is delta of x minus x0, but this x0 can be 0 wherever it is, right? So it doesn't matter. So basically we are saying that this kernel that we identified is the solution to a delta function input. Okay, so k of x0, x minus x0 t is nothing but e to the minus, sorry, x minus z0 t is at e to the x minus z0 the whole square. Okay, okay, x minus z0 the whole square by 4 alpha squared t divided by 2 alpha root pi t. This is the solution to the diffusion equation for a single delta function input. Now how this will look at it later times is that the delta function will slowly smooth over like this. I mean, it has to be symmetric. Okay, and then eventually it will become 0. Okay, it will finally become completely 0 everywhere. Now this way of writing the solution, okay, rather this way of writing the solution, where you write the solution to a differential PDE or no DE in terms of, this is the arbitrary initial condition. Now this, what is k of z minus x t, this is the solution to delta function forcing. Now such a kernel is called the Green's function. So Green's function is the solution to a differential equation, in this case to delta function forcing in the initial condition. Okay, now how do you understand? So what you have found is that you know what is k of x minus z or z minus x. This is solution to delta function initial condition, and the solution for any arbitrary initial condition is nothing but you're summing over, integrating is summing over, right, f of zeta times k of zeta minus x d zeta. It is like saying, if I have an arbitrary initial condition like this, at each I can think of this as a collection of delta functions like this. Okay, so the forcing for each of this will be f of c times dc, and then the solution for that initial condition is f of c dc times k times zeta minus x. So you have to sum up all the contributions due to various points, because it's a spatially distributed initial condition. So basically you can think of the solution to an arbitrarily spatially distributed initial condition as a linear superposition of the solution to delta function initial conditions, which is basically this, and this integral is basically like a summation. Okay, so this again happens because of linearity. Such a thing will not be possible if the governing equation was nonlinear. Okay, so this Green's function idea is very useful in solving linear partial differential equations, and it also gives a nice physical understanding as to how to think about the solution to an arbitrary initial condition as a superposition of solutions to a solution to a delta function initial condition based on various spatially distributed delta functions. Okay, I'll stop here, and in the next module we'll illustrate the use of a Laplace transform to solve a semi-infinite PDE. Thank you.